Tonight I'm going to be talking about the evidence that the universe is not expanding, despite what you may have heard elsewhere. And this presentation is going to have two parts. The first part is discussing the very recent work by myself and my colleagues, Riccardo Scarpa and Renato Falomo, that was published recently in the International Journal of Modern Physics, Part D. And then in the latter part, I'm going to survey some of the evidence developed by other researchers, as well as ourselves, that shed other light on why the universe is not expanding. So let me start with our own work, which is about the surface brightness test. Now, the surface brightness test was developed way back in 1930 by Tolman, so it's called the Tolman Test. And this is a simple geometric test. In a non-expanding space, the brightness of an object, its apparent brightness, goes down as a factor of 4 when its distance goes up by a factor of 2. But its size, its apparent area, also goes down by a factor of 4. So the ratio of these two numbers, which is called the surface brightness, is a constant. So that's a basic geometric property of non-expanding space. If space is expanding, and if the redshift is caused by that expansion, then there's a very different prediction, because the object was closer to us when it emitted its light than it is now. So it appears larger by a factor of 1 plus z, z being the redshift. So that's the factor of 1 plus z squared spreading out and dimming the light. And the individual photons are spread out in time as the spaces they travel through is stretched. So the net result is that the surface brightness, measured per unit frequency, is predicted to go down as 1 plus z cubed. So at high z, these are two very different predictions. So this is what we tried to test in this paper in International Journal of Modern Physics. We were testing with the Tolman test, the surface brightness test, whether the non-expanding model could be true. Now, to perform this test, we needed to determine the absolute magnitude, the absolute luminosity of the galaxies, because the surface brightness of a galaxy is known to vary in proportion or as a function of its luminosity. The brighter the galaxy, of course, the brighter its surface brightness. Now we have the observables, the apparent magnitude, and the redshift. To get the absolute magnitude in a Euclidean non-expanding model, we need a formula that derives the distance from the redshift. And we picked the formula, the very simple formula. D is proportional to the redshift at all z, for two reasons. One is, it's very well known that at low z, this proportionality holds, of course. We all know that. But in addition, a very important reason is that the prediction of this relationship for supernova, which is the measuring stick by which the expansion of the universe is actually determined, is exactly the same, almost exactly the same, as the prediction of the expanding universe model. So there's really no difference in the distance predictions. Let's see how that looks. In this chart, you see the dashed line, the upper line, which is barely separated from the other line. That is the prediction of the apparent magnitude versus Z for the supernova data on a non-expanding model with redshift proportional to distance. The solid line is the prediction of an expanding universe with dark matter and dark energy. And as you can see, they're very close. The dots and crosses are the actual observations of supernova. And the two models are an almost identical fit to the data. This follows from the mathematical conclusion that these two formulae are almost the same. And you can see this measured in various ways. The distance that's figured on the basis of the expanding universe and the distance that are figured on the basis of the non-expanding universe never differs by more than about 15%. And the distance modulus in magnitudes only varies by about 1/4 of a magnitude at most. So there really is no difference to speak of, which is a very striking result. I'll get back to that. But in practice, it means we can take distance out of the equation, basically say the distance is the same in the two models, and the luminosity is indeed the same. So given that, what did we do? We compared the surface brightnesses of 623 nearby disk or spiral galaxies measured with the GALEX satellite with 344 distant galaxies measured with Hubble in the Hubble Ultra Deep Field images. Now we took 8 pairs of samples, which in each case were matched for the wavelength band that they were observed at the origin of the radiation and for absolute luminosity. And we selected only very bright galaxies. Galaxies that were very bright in the UV, which gives us 2 advantages. One is the very bright galaxies can be observed all the way out to a Z of 5 and even beyond. And second of all, of course, they tend to be the bigger galaxies, so they're easier to resolve and measure. In addition, they're young galaxies. These are galaxies with very young stellar populations. So we're comparing babies with babies. We're not comparing baby galaxies with adult galaxies, so we don't have to look at evolution, even though these are very different time periods. They're very young galaxies. Now we did one further thing. We matched the telescope linear resolutions, the number of kiloparsecs each telescope could resolve at the distance it was observing, using our own model. Now the reason why we did this is that if galaxies are very small compared with the resolution, then if you have 2 very closely spaced galaxies, they will tend to be blurred by the lack of resolution into a single galaxy. And that will bias the surface brightness to dimmer levels. So you have to match those 2 resolutions. Now we used our own model to determine that matching, but as you'll see in a moment, that does not introduce a bias into the results. So when we did these comparisons, we ended up measuring the radius of each galaxy to get the surface area and measuring the apparent luminosity of each galaxy from the images. We combine these 2 measured quantities to get the surface brightness. So no calculations based on a model was involved in getting the surface brightness. That's directly from the observations. So in effect, what we're measuring is the size of galaxies that are the same luminosity. Same surface brightness means if you have the same luminosity, then the galaxies are the same size. So what did we find? Well, we found that there was a very good fit to the prediction of the non-expanding model, that the surface brightness is constant. Now, each of these dots shows one of the 8 comparisons. So what we're looking at is the difference between the mean surface brightness of the far sample minus the mean surface brightness of the near sample of galaxies, plotted against the redshift of the far sample of galaxies. So you can see from a redshift of 1 for the far galaxies out to a redshift of 5, it's very close to constant. And these error bars are 1 sigma, only statistical errors. And by the way, when I say nearby galaxies, these are all galaxies with Z less than 0.15, 0.15. Now, it can be objected, well, maybe we've biased the result by cutting off the sample at the lowest resolution that the images can be measured. What if too much of the sample is very small galaxies that we can't measure? Well, there's a simple way of taking into account the galaxies that are not resolved. That's to simply assume that these galaxies are smaller than the median galaxy in the sample. Now, of course, that's a very reasonable assumption. For the most part, they're smaller than any of the galaxies in the sample because they can't be resolved. So we say that their surface brightness is therefore greater than the median surface brightness in the sample. Then we can simply count how many unresolved images there are and end up with the median surface brightness for the entire sample, including the unresolved galaxies. And when we do this different measurement, median surface brightness, we come out with exact same result. As you can see, the dots are in a little different location, but again, they're very close to the 0 point. They don't vary very much from the 0 surface brightness difference that's predicted by the non-expanding model. Well, how close is close? Well, if we take the mean of all of the samples of the far galaxies and subtract the mean of the near galaxies, then all we get is 0.027 magnitudes per arc second squared, a very tiny and statistically insignificant difference. And the slope on Z is again statistically insignificant. The exact same thing if we take the median. The difference is 0.017 magnitude per arc second squared. Again, totally statistically insignificant. If we change this into a measure of size, which might be more intuitive, it means for equal luminosity, the radii of the near galaxies and those of the far galaxies are equal to within about 2%. So that's amazingly good agreement. Now, another objection that could be made is, well, maybe there's an observational bias. After all, we can only observe galaxies that are brighter than a certain minimum surface brightness, because if they're dimmer than this, even the Hubble telescope won't pick them up. So maybe we've simply created a window in which they have to be within this certain surface brightness. Well, we tested that, and it isn't the case. What we did was we took less luminous galaxies, galaxies that were not as have the absolute luminosity as our sample, and we determined observationally where the cutoff in surface brightness was. And the cutoff in surface brightness, as you can see from these red triangles, is about 28.5 magnitudes per arc second squared. That's where it suddenly falls off a Gaussian curve. Well, if you look at the sample that we actually took of these brighter galaxies, you can see the same dramatic fall off on the low side where the galaxies are unresolved. But of course, as I said, we've just taken those galaxies into account. But on the high side, on the dim side of the surface brightness curve, you can see that the Gaussian distribution has gone completely to zero before you reach 28.5 magnitudes. So the window here is wide open. It's open far enough, and these galaxies are bright enough so that none of them, even the dimmest, are cut off by observational limits. So this is very much of a real observation. Now, we also went back and looked at earlier studies of surface brightness in which authors had concluded that the non-expanding universe couldn't explain the results. And what we did was we applied our formula, the idea that the hypothesis that distance is proportional to z at all redshifts, to this old data. And when we applied that, we found that the data again confirmed our results. Now, these were studies done with a different sort of galaxy, with elliptical galaxies, and at lower redshift, from a redshift of about 1, which would be the red squares, and a redshift of 0.75, which is the green triangles, down to low redshift, which is the black dots. And here, surface brightness is plotted against radius. And what you see is, again, there's an extremely good confirmation that the surface brightness of the near and the far samples are the same. So our conclusion is that the Tolman test for surface brightness is completely consistent with a non-expanding Euclidean universe with distance proportional to redshift. Now, can this be explained in the expanding universe context? Well, people have tried to, because actually other people have observed this general tendency than we have. So what they say is, well, these galaxies at high redshift were very small, and basically their size evolved over time in such a way to exactly compensate for this surface brightness dimming. So they were smaller and had a greater surface brightness in the past, and they gradually lost that surface brightness by expanding, going towards the present. Well, what's wrong with size evolution, as it's called? Well, first of all, you have to accept that there's two really big coincidences. One is that the simple non-expanding universe theory fits the supernova data just as well as the expanding universe model. And second of all, you have to say that each of these redshifts, from a redshift of 1, or really 3/4, all the way out to 5, there is an exact compensation for the surface brightness dimming by this evolution. So that's really big coincidence. Second of all, size evolution has to accelerate. At high redshift, the size evolution is approximately proportional to the evolution of the size of the universe as a whole. So the galaxies are growing in proportion to the size of the universe. which actually they shouldn't be because they're gravitationally bound objects. But as you get closer to the present, for z less than 1, and especially for z less than 0.75, you have to have a steadily increasing acceleration so that by z of 0.75, the galaxies are growing as h of z to the minus 2.2. In other words, they're going at the square of the rate of the expansion of the universe as a whole. To fit these curves, you have to have at least 2 more parameters than the 0 parameters that we're using in the surface brightness. The growth has to be the same for ellipticals as for spirals. Now, in the case of ellipticals, it's the growth of the individual galaxies. They're individually getting bigger. In the case of the spirals, which are very young galaxies, they're babies, the babies are forming at larger and larger sizes. So you've got 2 different processes that are growing absolutely in step. And there's the question of what happened to these galaxies. You have observationally, given the expanding universe model, that you have extremely large, extremely dense elliptical galaxies. There's no way we could miss those galaxies in the present-day universe, but we don't observe them. Where did they go? And there's no physical mechanism that can make them grow like that. In addition, there's no physical mechanism that would make these ellipticals expand in this way. For example, it's been proposed that these are expanding because of mergers, collisions. But we can observe how many collisions are actually occurring in the universe, and there are 20 to 40 times too few mergers to allow this process to go forward at the rate that it's supposed to. By the way, there'll be references to all the work that I'm giving in the website that I'll show you at the end of the presentation. So you have this very large geometrical test that comes down in favor of a non-expanding universe. But of course you can say, well, in many other ways the expanding universe is a well-supported theory, so this is just some sort of anomaly. But what I want to say in the rest of this presentation is that there are observational contradictions to essentially every aspect of the predictions of the expanding universe model. I want to discuss 4 key ones tonight. The problem of lithium, the evidence against dark matter, the fact that there are 2 large-scale structures to have formed since the Big Bang, and the asymmetries in the cosmic background radiation and in other aspects of the universe. So first of all, let's look at lithium. If the universe went through a hot, dense period, then nuclear physics tells us that a certain amount of lithium must be formed. But if we actually observe old stars that have very little additional elements, metals like iron in them, and we measure spectroscopically the amount of lithium, we come out with a very different answer. Now, in this very telling chart, the prediction of the Big Bang nuclear synthesis theory is that solid line way up almost near the top of the chart. The actual observations most of them form this plateau called the Spite Plateau, which is a factor of 3 below these predictions. But what's much worse is that you have more and more stars that have lower and lower lithium abundance as you go to lower and lower values of the iron abundance. So the purer the star is, and presumably the earlier it formed in the history of our galaxies, the less the lithium content. And that's entirely consistent with the notion that there was no lithium before the galaxy formed, which is completely in contradiction with Big Bang nucleosynthesis. But it's completely consistent with the idea that if there was no Big Bang, then lithium comes out of processes occurring within our own galaxy and within other galaxies. Lithium forms in two ways. We know this. One is by cosmic rays breaking apart carbon, nitrogen, oxygen, and other molecules, and thus building up the lithium. And second, certain stars, AGB giants, produce lithium in their own atmospheres and blow that off into space. So I and other people developed theories based purely on thermonuclear reactions occurring within stars and reactions in cosmic rays that predicted not only the amount of lithium that we observe, and that lithium would build up from zero, but also the amount of deuterium and the amount of helium. Helium, of course, is the main product of thermonuclear reactions in stars, and deuterium is also a product of cosmic ray interactions. So again, this is a contradiction that's very difficult to explain in an expanding model, but flows naturally and was predicted many decades ago in the non-expanding models. Now there's the question of dark matter. Dark matter is central to the current concordance cosmology. But there's good evidence that dark matter cannot exist in the amounts that is predicted by this theory. One piece of evidence is simply the lack of high velocities that we observe among galaxies. Given the inhomogeneity we see, if there was as much gravitating matter as is predicted by dark matter theories, you would expect much higher velocities than are in fact observed. Second of all, there's the case of the alignment of the satellites of our own galaxy and of our nearby neighbor Andromeda. In both cases, as this chart shows, the satellite galaxies are arranged in disks. Now, that's extremely difficult to explain if the gravitational field is essentially spherical, as it must be if it was formed by non-interacting dark matter particles. But if the gravitational field is in fact formed by ordinary baryons, ordinary ions and electrons, then a disk formation is exactly what you would expect. So these two factors, as well as many others, add up to strong evidence against dark matter. And again, there are other explanations for the phenomena dark matter attempts to explain, such as the high velocities of rotation of spiral galaxies. First of all, there's the whole theory of modified Newtonian dynamics. That's the idea that at low accelerations, there's a small modification to Newtonian, to gravitation, that explains this apparent excess of gravitating force. There's a lot of good evidence that's been developed by other researchers for this hypothesis, especially the fact that the deviation from what you would expect of these velocity curves tracks exactly, for all of these galaxies, the acceleration due to gravity, which is what the Mon theory predicts. In addition, simulations of galaxies purely based on plasma effects has also produced these characteristic flat velocity curves, because the magnetic fields are actually sweeping along the plasma. And it's the plasma that we measure far out in the galaxies using radio waves. It's that Doppler shift, not the Doppler shift of the stars. So again, there are simpler theories to explain these same phenomena. The third problem, observational problem of the expanding universe model, is that we observe in many, many different ways large-scale structures that simply are much larger than those predicted by the Big Bang theory, and second of all, must have taken much too long to form, much longer than the time available, because we can measure the velocities actually available right now. And if you put that together with the size of these objects, you get formation periods, even taking into account the expansion of the universe, that are much longer than 14 billion years. This is just one illustration that I chose mainly because it looks nice of the concentration of quasars that was observed by a group of researchers. And you can see that these quasar concentrations extend over hundreds of megaparsecs, much larger than the 50 or 70 megaparsecs, which is considered to be the limit for formation of large-scale structures. In this case, too, 30 years ago, or almost 30 years ago, I developed non-parametric, no free parameter theories that actually predicted these large-scale structures simply by taking plasma physics and the tendency of plasmas to filament and combining that with gravitation. And if you combine these things, you end up with the prediction of large-scale structures based on their gravitating velocity, which is in the vertical dimension. The vertical axis is their gravitational velocities. And the horizontal dimension is the product of the distance between the objects, their spacing, and the average density of matter if these objects were spread out to that spacing. In other words, the density of the cloud from which these objects contracted. And as you can see, from clusters of galaxies to galaxies down to individual stars, the structures all fall along these lines, which in this paper that was published back in 1986 were developed without any free parameters from basic plasma physics plus gravitation. And this paper predicted from the intersection up here in the upper right the very large-scale structures, hundreds of megaparsecs, that have now subsequently been observed. So these were actual predictions long before the observations that were verified. Now, of course, these very large objects would take hundreds of billions of years to form, which would be an enormous problem in an expanding universe, but would not be a problem in a non-expanding universe, which presumably did not have an origin in time. Final contradiction is in the alignments and asymmetries in the cosmic background radiation. Now, the cosmic background radiation is considered a great proof of the existence of the Big Bang. But inflation, which has again become an integral part of the expanding universe theory, predicts that all asymmetries between one side of the sky and the other would have been wiped out by inflation. So it strongly predicts that there are no axes of symmetry, there's no rotation for the galaxy we can see. But what we observe in the cosmic background radiation and other evidence is that there are such special axes. This illustration shows that the dipole, the quadrupole, in the octopole, the lowest modes of the anisotropies in the cosmic microwave background, are actually closely aligned. So this sets up a special axis which should not exist. But that's not the only problem. If we look at all of the low modes up to 10 or 30 on the sky, the predictions of the concordance model are in fact a very poor fit, as you can see, to the actual data. The low mode data does not fit this 6-parameter theory. What's worse is the lack of fit is different on the two sides of the two hemispheres of the sky. As you can see, the low power hemisphere, this red line, shows very great deviations from this line, which is the predictions, and pretty significant deviations from the other hemisphere as well. Now, the statistical variance on this scale is a few hundred, 200 at this point, and you can see this goes down almost to 0. So it's many standard deviations away at many points. That sort of asymmetry simply should not exist if inflation had occurred. Now, in all of these cases, there has been a knowledge of some of these contradictions, and the reaction has been to add more free parameters to the theory. As a matter of fact, we saw this quite recently. People are aware of the publicity over the biceps results, which were taken or were advertised as a proof of inflation. But the actual waves that were hypothesized to have created the biceps results are incompatible with the waves that are hypothesized to create the Planck results. Now, there have been a couple of dozen papers published in a short time since the biceps results, and all of them are attempting to resolve this contradiction by introducing more free parameters. And there's a big methodological problem with this, which Mike Disney pointed out in this table. If a theory is to be predictive, it must make more predictions than free parameters. If you take an excellent theory like Maxwell's theory of electromagnetism, it has one free parameter, the speed of light, but you can make billions of predictions from it, very accurate predictions that allow us to be confident that we can switch on the light. The same thing with quantum mechanics. It has one free parameter, Planck's constant, but you can make billions of predictions, including that gadgets like the computer on which we're viewing this slideshow will work. In cosmology, you have a very different situation. As new observations have come about, new free parameters have been added to explain them in such a way that you've never had a situation where there are more observations than free parameters. As this chart shows, this is the number of parameters, free parameters, which by Dr. Disney's count is now up to 20. This is the number of new observations, and this is the difference between them. And as you can see from this column, it's been consistently negative, which means there are more free parameters than there are observations. The expanding universe model does not have any predictive power. So basically what we've got is not only two hypotheses, we've got two methods of looking at the universe. In the expanding universe model, we have an unlimited production of free parameters of new hypothetical entities and no predictive power. In the non-expanding model, we introduce new parameters only in the most minimal possible way, such as the Hubble parameter. And we try to explain all of the phenomena of cosmology as much as possible using well-tested laws that we can extrapolate outward from the laboratory. So this has high predictive power. The problem is only one of these methods is receiving funding. The first method has 100% of the funding, and the second method has 0%. Now, it is impossible to get science done without funding. I hope from what I've conveyed this evening, you will agree that some part of the funding has to be allocated to the alternative, non-expanding approach. Now, finally, you can ask, what does it matter? Now, maybe for this audience, that's a funny question, of course, to you. All of us, it matters whether the universe is expanding or not. But what does it matter in general? There was a famous question that the fictional Sherlock Holmes put to Watson after Watson had explained to Holmes that the Earth went around the sun. And Holmes said, "What the devil difference does it make to me whether the Earth goes around the sun or the sun goes around the Earth?" Well, actually, that was a rather ignorant question on the part of Sherlock Holmes, because it made a tremendous amount of difference. In the Ptolemaic system, with its multiple epicycles, multiple free parameters, it was impossible to predict exactly where the moon would be at any given time in the future. With the Newtonian laws of gravitation, based on Kepler's hypothesis of the structure of the solar system, you could exactly predict, and it was, over the decades, exactly calculated where the moon was on the sky at any time in the future. Why did that matter? If you know where the moon was, then you know what your time is. If you know what your time is, then by measuring where the sun is, you know your longitude, you know your location. So the navigation then made possible the trade that allowed the standard of living that Britain enjoyed at the time of Arthur Conan Doyle. That was all made possible by the navigation from the theories of the Copernican universe, the Keplerian universe, the Newtonian universe. It would have been impossible with the Ptolemaic theories. So method matters. And I think it matters today, too. I think that because of the very high public profile of cosmology, people get the wrong idea of science. They get the idea that science is about writing equations on the board and deciding which ones are more beautiful, and then fitting your equations by free parameters to the observations, instead of going from the observations to derive theories that can be used to predict a huge number of phenomena. And finally, it matters in very specific ways. The plasma theory that I and my colleagues used to develop this line of research is the same plasma theory that I'm using in my main line of research, which is to develop fusion power as a cheap, clean, unlimited source of energy, as I mentioned in my earlier presentation to the Scientific Society a few days ago. Today, as in the past, we can learn from the cosmos. We can learn from these vast filaments that are forming large-scale structures, how filaments behave in a laboratory. And we can learn from their behavior in the laboratory how they behave in the cosmos. This link between the cosmos and Earth has been broken in conventional cosmology and must be reformed. So that basically sums things up. If people want to learn more and follow up on the references that I've made reference to in this presentation, then please visit us at lppfusion.com. And in particular, you can click on the link to the news about the non-expanding universe evidence to go to a document called The Growing Case Against the Big Bang, and there you'll see links to all the papers that I've referenced in this presentation. So that's about it. I'm a little over time, so thank you very much, and I'll take all your questions. Thank you.